Hey folks, Mash is back, and today I'll be doing the 2019 Paper 1 Chemistry, as this will be the multi-choice. Only 25 marks, so don't worry too much about this. And hey, if you don't know a question, you can just put something random. Let's get cracking. Now, first question here, we've got hydrogen will form a non-polar covalent bond with an element that has the electronegativity of what? So, non-polar means that there'll be no permanent dipole in the molecule. And the only way you have that is that you have two atoms that don't have that have the same electronegativity. Now we know one of them is hydrogen, which is 2.2, which means if there wasn't a dipole, the other one would have to have 2.2. And well, how do I know it's 2.2? Am I just pulling it out of the book? Well, we go over to our data booklet, which is probably the most very important. I'm going to have to go and find the here we go. So we're going to go to ionization energies and electronegativities as selected elements. And if you go around here, you can see on the electropolling scale, hydrogen's electronegativity is 2.2. So there we go. Obviously, that means our answer must be C. Now, in a similar vein, which of the following is a polar molecule? We've got CC4, NH3, CO2, and CH4. So this one is going to be about structure, because you notice all of these actually do have dipolar bonds, but that doesn't necessarily mean they are polar molecules. So I'm going to go and draw these out real quick. So carbon tetrachloride looks like. Let's go and draw that out. So this would be, I think this would be tetronic. This would be have a tetrate structure. I can't remember the exact name. Oh, sorry. But whenever we have 4 bonds to a carbon, what we actually get is stuff that looks like this. So I need to go and then it's the opposite way. Ain't it? Right, and if you look at this, right, all these carbon atoms, they kind of balance each other out. It's like equal around. So there's no one direction that chlorine would the dipolar would go to. So you know if you're pulling on an object in all directions, it's not going to move. So that means that this is not a polar molecule because it's symmetric. Now, what about ammonia? So ammonia, in a similar vein, it is still got that 3D structure. I'll see if I can pull off, but if you can see here, it's quite clear actually that we have a dipole going up the way, because it looks like a bit of a pyramid. It's pyramidal. So that means that since nitrogen has a higher electronegativity than hydrogen, that means this side will have a nice negative side, and then this one will be a positive. So we already think that it's probably going to be B, but let's just double check our work by seeing if C or D could make polar molecules. So carbon dioxide would look good if you make the erroneous assumption that it would be like water, and you would have something like this, but carbon doesn't work like that. That's false. So what carbon dioxide actually looks is a double bond with oxygen on both sides. As you can see here, it's a linear molecule. It's not changing in structure, which means there's no per dipole, so that's rubbish as well. So we know it's not carbon dioxide. And then methane is the same structure as methane tetrachloro, whatever it's called, as letter A, which means that this one, it's just the same as this if you replace all the chlorines with hydrogens, so it's also garbage. So yeah, we've proven beyond any reasonable doubt that 2 has to be B. So, question 3. Which of the following is most likely to act as a reduction agent? Is it carbon monoxide, magnesium oxide, hydrogen peroxide, or chromium oxide, or whatever it's called? It might be dichromium. I can't remember. What we're going to do is figure this out, is go on to our data booklet. We'll have the electrical chemical series of standard reduction pentals. So, important thing to realize about this is that at the top we have our best reduction agents, and at the bottom we have our best oxidation agents. You notice here, right? You already see. Oh well, that's hydrogen peroxide. That's magnesium oxide. That's dichromium oxide. But all these down here, very, very near the best oxidation agents. So these are all pretty unlikely to go through. But carbon monoxide, if you remember, it's used for refining metal ores, which is reduction, right? So that means that it's probably going to be carbon monoxide. And there's also carbon monoxide can also act as a reducing agent or oxidation agent. It's kind of in the middle, but all these below it, according to our table here, are all very, very likely to act as oxidation agents rather than reducing agents. So carbon monoxide is the correct answer there. So we'll move on to 4. The following reactions take place when nitric acid is added to zinc. How many moles of zinc are oxidized by 1 mole of nitrate? So how are we going to figure this out? Well, what we want to do is combine these two equations to a single redox. And to do that, we basically want to get rid of these electrons. We don't like electrons in redox. So if we have a look at this, we're like, okay, well, if I times this one by 2, we'll have 6 electrons there on the left side. And if I times this one by 3, we'll have 6 electrons on this side, which means they'll both cancel out. So if we write that out, it'll be N of 3 minus AQ, and then 8 H plus, and then I'll probably have to do another line, and then plus zinc times 3, so it'll be 3 atoms of zinc. What does that get us? Well, that gets us nitrous oxide plus 4 water, and then plus 3 zinc 2 plus ions. So, well, they're writing these that stated symbol. What does this mean? Well, that means that 2 nitrous oxide, 2 moles of this will make 3 moles, or will oxidize 3 moles of zinc, which means if 2 moles make 3, that must mean that 1 mole would be 1.5, which means the answer must be C. We'll move on to question 5 now. Which of the following compounds is a tertiary alcohol? Now, tertiary alcohol means that the hydroxyl group, the OH, will be connected to a carbon, which is itself connected to 3 other carbons, like this. So, how we're going to find this out? Well, what I'll do here is, we know it's got to be a branch chain, because if we look at our diagram, I'll have to redraw. You know, that's not a linear thing. That's going to be a branch, which means we can get rid of C already, because that's not a branch chain molecule. But remember, if it is a branch chain, the hydroxyl group will have to be on the same carbon as the branch. So we're looking for something that has its hydroxyl number the same as its branch number. And if we look at here, right, that's 1, that's 2, that's garbage. That's 3, that's 2, that's garbage. Oh, B, its branch is the same as its hydroxyl. And you can, if you want, you can draw out all the structures of these that you can see for yourself, but that's the easier way to do it. And we'll move on to question 6. So, we have this molecule here. Which of the following can be produced by partial hydrolysis of X? And remember, hydrolysis basically just means splitting with water, right? So that means we're going to split these molecules into molecules, but it's also partial. So instead of splitting it completely, we're only going to split 1 or 2 bonds, you know? Because I see here we've got 2 links here, amide links. So since it's only partial, we're only going to cut 1 of these, which is why in our diagrams you see that there's still 1 remaining. So that means that we have to find molecules that be caused by either one of these getting split. So let's go and have a look down in our down here just to see if we can see any obvious ones. So if we look at, yeah, we can just go through them. Start from the bottom up. I wonder why I'm doing that. We'll see. We can just start comparing it to this one. So you can see here, this one doesn't make any sense because you don't find any of these functional groups in that order, right? Because if it was this molecule here, you would expect to find a CH and then this group up here, but it isn't. And if it was this over here, you'd expect to have a CH3, but you find that. So D's garbage. If we move on to C, this side looks okay. It's looking fine, but then it's connected directly to this bit here, when it should be ending off in a CO2, because we'll be, in this case, we should be cutting that, the right thing. So C doesn't look good either. What about B? So B, it looks okay, sort of okay from here, because like we can say, okay, well, if we're cutting that, then we would have CO2, then we would have this amide link. But if we go over here, we have this. We do have CH bracket CH3 2. We don't have the CH3, so B's bad as well. So process of elimination, it has to be A. We can prove it. So we see that we've got this functional group here. That's same over here, same over here. This down here. So all this here is the same, and all we have stuck on the ends is the hydrolysis product, which is the nitrogen with two hydrogens bonded to it, which is what we would get if we cut that. So long-winded explanation, but 6 is A. Move on to 7. So a compound with a molecular formula C6H12O2 could be what? So we'll start with the easy stuff. Let's go and have a look through here and count up all the different carbon atoms. So pentoethanate, pento means 5, ethanol means 2, which means total will be 7, so can't be A. Hexanon, that makes sense. That's 6, so this could be it. Methylpentanol, that's 1 and 5, so yeah, it can be 6. And hexanoic acid also could be 6 as well. Next up, what we want to do is go through our general formulas. And straight away, well, an alcohol, right? An alcohol's main general function is an OH group, and you can represent alcohols as this standard figure. You don't just always write OH at the end. So that's just kind of a standard that's used to make things communicating a bit easier. But you can write it as this pure molecular formula here. But why do we have an extra O atom, oxygen atom? Because it doesn't say diol, it just says one. So it should only have one of these hydroxyl groups. So it should only have one oxygen atom. So C's out for now. And the same principle applies for the ketone, the hexa-2-one. The 2-one applies, we have a double bonded oxygen. And it doesn't say dione or anything weird. We've just specifies that we have one double bonded oxygen, and we clearly have 2. So B's out as well, which means it has to be hexanoic acid. And if we pull up the general formula for carboxylic acids is H2N O2, which it directly matches with that. And the reason that is that the carboxylic group always contains something along the lines of this, which, yes, you'd always have 2 oxygens. So yeah, it would be D, hexanoic acid. Move on to 8. Compound X reacts with hot copper 2 oxide, and the resulting product did not give a color change when heated with Fettling solution. So compound X could be what? So copper 2 oxide, that would be oxidizing the chemical, right? So whatever compound X is would be oxidizing it with copper 2 oxide. So let's see if we can actually oxidize any of these. So pentanoic acid, that's already at the end of the oxidation chain, I suppose, because you go from a regular hydrocarbon, then you go alcohol, and then you go then you go to a ketone or aldehyde, and then you go to a carboxylic acid. Carboxylic acid you can't oxidize anymore. So pentanoic acid is out. Pentanthreone, that is a ketone. So it'd be yada yada, I'll draw the whole thing. But you'd have a carbonyl group in the center. And the thing with that is, if you have a carbonyl group in the center, you can't oxidize it further than this, because there's nowhere for any extra oxygen atoms to go onto. So ketones can't be oxidized further. And then pentan 2 and pentan 1 also alcohols can be oxidized, which is fantastic. So what would happen is you'd have your OH group and you transform it into a carbonyl group, which yeah, you can do for both of them. But the thing is, with pentan 1O, you'd get an aldehyde. Yeah, I'll type it out maybe. No one can actually read that. You'd get an aldehyde if you did with pentan 1O, because you'd have the carbonyl group on the on one of the terminal carbons, not the ends. But if you did it with pentan 2O, what would you get? Well, you would get a ketone, as we've already established, where you have a double bonded oxygen in the middle of the hydrocarbon chain. So that means that we can't oxidize ketones any further, which is important because Fettling solution would only give a color change if you could oxidize the product, even the this product further. So you can oxidize an aldehyde to a carboxylic acid, which means that it would give a color change for Fettling solution. But a ketone you can't oxidize, which means it has to be B, because it did not give a color change for Fettling solution. Okay, the structure of pyruvate acid is shown. Which of the following is the correct systematic name of pyruvate acid? Is it pentanoic acid, 2,2,2-trimethylmantonic acid, 2-FO? You know, you get the gist. So when we want to do systematic names of things, we want to find of hydrocarbons. We want to find the shortest chain length possible. And ideally we want the functional group to be on the lowest number of that chain. So I'm having a look at this, I'm saying, okay, well that's a carboxylic group there. So I'm gonna start there, let's say, and then I'm gonna say I'm gonna move along this chain and see if we can find the shortest answer. And well, see here, it looks like it's going to be 3, because I can't make it any more. If I went here, it'd be 3. If I went here, it'd be 3. So we know that it's going to be based off of 3, which means scrub that, and we're left with either these two. And yeah, we can just use what we can do here is we can just say, well, ethyl would have a branch chain over here, which it wouldn't make any sense, because you'd prefer to have it would be the same as butane with a methyl group, but also 2, it's not in this diagram here, it's 2 methyl groups not combined together, so that one's garbage as well, leaving us the only answer of 2,2-dimethylprotonate acid. That makes sense. We've got 2 methyl groups, but they're both on carbon number 2, because we'd say, well, that's carbon, that carbon's 1, that carbon's 2, that carbon's 3, so it has to be D. Question 10. The table shows 4 compounds that contribute to the aroma of spices. Which compound is not derived from a terpene? So remember, a terpene is a fancy name for isoprene, which is itself the standard name of a chemical we call, well, so we can remember it, 2-methyl-butane, 1,3-diene. Now, important thing to notice here is that methyl and butane, that means it's 1 plus 4, which means there's 5 carbon atoms, right? And a terpene is just any of these, any chemical that is derived from stacking lots of these isoprene molecules together. But since each isoprene molecule has 5 carbon atoms, that means they all must be a multiple of 5 carbon atoms. So, for example, an A would have 2 of them stuck together to create a C10. And we can see A, B, and C are all C10, C10, C10. But D is C9, which means it can't be derived from a terpene because 2 isoprenes wouldn't be able to equal 9. So it has to be D because it's asking for what is not derived from a terpene. Move on to 11. Which reaction can be classified as reduction? So remember, we should probably write this out. In the reduction series, what you can do, you go alcohol. If you oxidize the alcohol, you would get a aldehyde / ketone. Ketones can't be oxidized any further, but we'll put them on regardless, and then we'll get carboxylic acid. So this is the direction of oxidation. Oxidation goes to the right. But this is reduction, which is the opposite of oxidation, so it'll actually be going to the left. So we need to find something that goes to the left of these reactions. So methanol, that's an alcohol to a carboxylic acid. That's going along the chain. And propanol, that's an aldehyde going to an acid as well. So not good either. We have a ketone going to a alcohol. Oh, that is going backwards. Maybe it's C. And then we have an alcohol going to a ketone, which is, yep, going the same way. So it looks like C would be it, because it's going from an aldehyde to an alcohol. A ketone to an alcohol, sorry. Which is reduction. A secondary amine has 2 carbon atoms directly bonded to the nitrogen atom. Which of the following is a secondary amine? So, yeah, we'll just have, this one's pretty easy. It's very self-explanatory. 2 carbon atoms directly bonded to the nitrogen, directly bonded, okay? So, for example, A, this is garbage. There's only 1 carbon atom. So it can't be this one. This one here, ooh, 2 carbon atoms, maybe. Let's keep it in the back of our mind. This one, oh, well, it looks like there's like 3 of them. That's garbage. And then if we look at this, this is only 1 yet again. So that means it must be B. Move on to 13. The number of moles of ions in 1 mole of copper 2 phosphate is what? So, well, it tells us the valence number of copper in this case, which is copper 2 plus. So what is phosphate? Well, you can either memorize it, well, I know it's 3 negative, or you can go find the formula of selected ions and find it is 3 negative here. So that means that it's 0.4, ain't it? That means that if we want to create this ionic molecule here, we'd have to have 3. The molar ratio must be 3 to 2. So they create a neutral molecule. Okay, so that's all well and good. That means that 1 mole of this ionic molecule must contain 3 moles of copper and 2 moles of phosphate, which means 2 plus 3 is 5, or D. 14. Which are the following gas samples of the same volume as 4 grams of methane? So this is basically asking, because all the volumes are measured at the same temperature and pressure, that means that they're equal to moles, right? So it's basically asking which of the following samples have the same moles as 4 grams of methane. And we can calculate the number of moles. We can go and pull out N equals M over Fm. Now we've got 4 grams of methane, and the formula mass, well, that's 12 because carbon's 12, and then it's got 4 hydrogen atoms, so it'd be 12 plus 4, so 4 over 16, which is 1 over 4 if you simplify it, right? So we're looking for something with 1 over 4 moles, and well, let's go through it. Bottom from the top again, no, why not? So chlorine is 35.5, and we're going to go to our data sheet and find the mass table. So chlorine, remember, is diatomic, so each mole of it would actually be of 2 chlorine atoms. So we go over here. Oh yeah, we've got 35.5, but and that would mean that a mole of it would actually be 71 chlorine, but that would only be a half, right? So this was, because this is would be a half, because a whole was 71 grams, and then we've actually only got 35.5, which would be one half, which is not what we want, so it can't be D. 3.5 grams of nitrogen. Well, at a passive glance, this has actually fooled me before. Nitrogen, oh, it's 14, and well, 3.5 is a quarter of 14. But remember, nitrogen is a diatomic element. It's got its triple bonded to itself, which means that its total formula mass is actually 28. So 3.5 is 1/8, not 1/4. That's bad as well. 1 gram of hydrogen. Well, hydrogen, famously, its formula mass is just 1, which is why I've just said it 4 here for 1, which means 1 gram of hydrogen is 1 mole of hydrogen. So that means B can't be either. But 1 gram of helium, and remember helium, look over here, you may not suspect it because it's a lot of people think helium-2, but remember the most common isotope of helium has got 2 neutrons and 2 protons, which means that it's got 4. That's a 4. And if we plug it in here, we have, well, it's got 1 gram, and its formula mass is 4, which is the same as our 4 grams of methane. So it's going to be A. Oh, magnesium carbonate reacts with nitric acid. 0.05 moles of magnesium carbonate was added to a solution containing 0.06 moles of nitrate. If I scroll over to the side, acid. Which of the following statements is true? Okay, so I'm already seeing stuff like excess in here in some of the answers. So what I'm going to do is I'm just going to see how many, I'm going to see if any of these compounds are in excess or not. So it says 0.05 of this magnesium carbonate, and then 0.06 of this. But it's clearly see if this is 0.05, then to fully react with it, you'd have to have 0.1, because it's 2 times that. And we don't have 0.1, we have 0.06, which means that magnesium carbonate is in excess. So if you already knew that, you could. So C is looking likely, because that is true, it is in excess. But let's double check that it is rightly by 0.02. So, how to figure this out? Well, we'll do the opposite thing. So if you have 0.06 here of this nitric acid, well, if we divide it by 2 to figure out how many magnesium carbonate we would need, would get 0.06 divided by 2 would be 0.03. Which means, yes, it is in excess by 0.02 mole. So the answer is C. So let's make sure we're right by going through the other statements, seeing if they're right or not. So we know that we're only going to react 0.03 of this magnesium carbonate, which means 0.05 moles of carbon dioxide is not going to be produced because 1 mole in this reaction is only 0.03, which means there will be 0.03 moles of carbon dioxide produced. Similar thing will be going for magnesium nitrate. There will only be 0.03 of the stuff, because it's not. It would only be 0.05 actually if we actually reacted all of magnesium carbonate, unfortunately. So yeah, that B is also garbage for similar reasons. Nitric acid is not in excess by 0.01 because it's a limiting factor. If we had more nitric acid, we could react more of the magnesium carbonate. That's bad as well. So it has to be C. And we'll move on to 16. In which of the following diagrams does the dotted line represent a potential permanent dipole interaction between propanone molecules? So we'll go through this. We can start with A. It's easier to eliminate it because oxygens are pretty high negativity and have pretty high electronegativity, which means this side will be having a minus, this side will also be having a minus, and well, opposites attract, same repel, which means that A cannot be right. B looks a bit more likely because at least they've got the dipoles the way right round, but remember the CH dipole is a lot weaker than the CO dipole, because the hydrogen's got some more similar electronegativity to carbon than oxygen does. So it's not really likely to actually form because these are permanent dipole reactions. So they're fairly stable. C is just completely insane. It's CH to CH. Oh, not great. That's remember CH and CH. That's well, that's just bad. I'm sorry. That's just horrific. And the same thing applies. Carbon, I believe, if I go and check our table, which is on, where is it? Here we go. Hydrogen, it's got electronegativity of 2.2, and then carbon has 2.6. So that means that it's two positives attracting each other, which is, of course, not something that can happen. So it cannot be C. When you look at D, and well, that's good because we've got our strongest, our most powerful dipole of oxygen and carbon, and they're connected in the correct way. Which means it's going to be D. I will move on to 17. Iron can be produced from iron-free oxide. The atom economy for this production of iron is what? So remember, atom economy is calculation of atom eco, I think. Well, we have mass of the desired products. Sorry, my handwriting is appalling. I'll go and just write it all out. Type it all out. We have mass of desired products over mass of reactants. So this is atom economy, essentially measuring how much useful stuff you get out of your reaction compared to what you put in, and then times by hundreds, but whatever. So if I go and run this through our calculator, we can see what we get. So it's production of iron oxide. Sorry, let me just go and put this on top. It's production of iron oxide, which means we can start by putting which we can start by putting the formula mass on top. And remember, this is going to be a bit confusing for most people, but this atom economy is the only calculation where you're going to actually use these numbers at the front of one to in the actual calculation itself. I'll deal with them when we get into it, but I'll just make this a bit bigger. So 4. Now, you put brackets, don't I? 4 times 55.8, and then we're going to divide it by mass of reactants. So that would be 2 times 159.6 plus 3 times 12. What we get here, we get this number, and then we're going to multiply by 100 to get the percentage, and we get 62.83, which is B. And there we go. Right, move on to 18 now. 100 centimeters cubes of propene is mixed with 600 cubes of oxygen, and the mixture is ignited. At the end of the reaction, the total volume of gas would be what? So this is kind of just another molar questions. They love having these molar questions, which are just and disguising them really. So what we can learn from this, we can learn that 1 mole in this particular reaction is 100 cubic centimeters. Because that's what it, we can see here that 100 centimeters of propane, and there's 100 cubic centimeters of propane right there. And it's mixed with 600 cubic centimeters of oxygen, but it only needs 500 cubic centimeters because 5 times 100 is 500. So we're actually going to have 100 oxygen left over. Okay, remember that for later. Then all that gets turned into carbon dioxide and water. But water is it's a liquid, so we're just going to outright ignore that because we want total volume of gas. At room temperature, water is a liquid, so it wouldn't count towards this. So that means we only have 3 moles of carbon dioxide, but as I established, 1 mole of stuff in reaction is 300 cubic centimeters. So that's what we get. We get 300 cubic centimeters of carbon dioxide and 100 cubic centimeters of leftover oxygen, which means You're never going to believe this. 100 plus 300 is 400. And that's where you put for your answer. So yeah, a lot of these, you make sure to check if there's going to be any leftover gases or not. Move on to 19. A two-step reaction is shown below. The first step will give a yield of 60% and the second step a yield of 90%. And this one is going to be quite easy. We just need to times two yields together. So 60% is 0.6 effectively, and then 90% is 0.9, times together 0.54, which is 54%. If you think about it, if I put 100 things in, to begin with, it has a yield of 60%, so we get 60% out. And then next process only has a yield of 90%, so it'll be 90% times this 60, which would be, you know, imagine taking away a tenth of 60. 10th of 60 is 6, which if we take away 6, we get 54. So we have 54 remaining, so the total yield is 54%. The volume of hydrogen gas given off against time when an excess of zinc lumps is added to 100 cubic centimeters of 1 molar per litre hydrochloric acid is shown. You can see here it's got a nice gradient, it goes out and it kind of plateaus. Which of the following graphs should show the volume of hydrogen gas given up with excess of zinc powder is added to 50 cubic centimeters of 1 molar per litre hydrochloric acid. So what we can tell from this is, well, zinc powder has way more surface area than zinc lumps, which means that reaction rate increases, right? Because there's more surface area of particles to bump into. But, au contraire, it only says 100 cubic centimeters rather than 50 cubic centimeters, which means there's less stuff to react to. And it's excess of zinc powder, so we're going to react with all this hydrochloric acid here, which means it's going to be half as much product produced. Okay, so now we just need to we've got these golden rules here. Now we just need to have a look at these graphs and see if any of them make any sense. So this one has higher reaction rate. A has higher reaction rate, but it goes to the same level as before, which means that it's garbage because we've said there's only less product is produced. A is bad. B has half as much product, but it has a slower gradient. We've all established reaction rate is faster. C is half and has a faster gradient, so I'm gonna put C. But just to double check, we'll do D, and it's the same gradient, but it goes D. It's like the same graph, ain't it? It says D would be if nothing changes. So yeah, garbage. I'll move on to 21. Consider the reaction pathway shown below, with WX as an enthalpy change of A, W to Z has enthalpy change of B, Z to X has enthalpy change of C, and Z to Y, Y to X has an enthalpy change of C, and then C to Y has an enthalpy change of D. According to Hess's law, it's what. And this, if you do maths and you do vectors, this will be pretty simple for you. Because all we need to do is kind of go round here. So if we want to go from W to X, that would just be A. And then if we go backwards along a vector or an enthalpy change, that would be C but minus, so it'll be A minus C. And then we have to go backwards across D again, which will be A minus C minus D, which would, you know, B equals A minus A, B equals A minus C minus D. So it'll be A. 22. Which of the following is not a factor that affects the rate of reaction of a reaction? So we'll go through this. Activated energy, that absolutely does affect the rate of reaction. If you have, that's why catalysts increase rate of reaction, because they reduce the activation energy by providing a alternative reaction pathway. Kinetic energy reacting molecules, that's basically just a stupid way for a fancy way to say temperature, which of course, if I heat something up, it's going to react faster usually. So yeah, but yeah, temperature absolutely affects the rate of reaction. Concentration reactants, yeah, 100%. If I use very super concentrated hydrochloric acid, it's going to react faster than super lame weak acid you get in chemistry class. So process elimination has to be D. Enthalpy change of reaction, well, that makes sense because enthalpy change just means the reaction is exothermic or endothermic and how much energy it produces, which no one cares in terms of reaction rate. So it has to be D because it's the only one that's not a factor. In which the following reactions would the yield of product be increased by lowering the pressure? So when you want to lower the pressure, remember, the system will change the equilibrium to try and fix the system in a way, and they will do so by producing more moles of gas. So in essence, what we need to find is an equation that so all these are orientated that we want to get yield of product. So all these on the right side of products, we want to get a system that we have a low number of moles, and then they would get turned into a higher number of moles of product. So we're going to have a look through here. That's 1 here, that's 1 here, and that's 2. So that's equal number of moles to both sides. Can't be A. 1 mole here, 3 moles here, so 4 on this side, and it gets turned into 2, which, yeah, you don't want it, that's reducing it, so it can't be that. So this is 1 mole gets turned into 2 moles of gas. Oh, that's increasing, so maybe it could be that one. And then 1 mole, 3 moles get turned to 1, so yeah, it can't be that one. And it's got to be C. 24. The graph shows how the distribution of kinetic energies for a reaction involving 2 gases. So you can see here we've got this nice curve, which graph would show the effect of raising temperature. A looks pretty likely so far because we've got it's the same amount of volume, same amount of area, which means it's the same total number of molecules in the thing, which makes sense. If you increase the temperature of something, you're not adding extra molecules, extra particles to it, but there's more particles that are above the kinetic energy threshold, the activation energy, so more react. So yeah, A looking pretty likely. Let's double check our answer though. B is insane. If you increase the temperature of something, you don't add more particles at a lower temperature, lower kinetic energy. That's silly. C is reducing the activation energy, which isn't true either. Increasing the temperature moves more particles to be above the activation energy. It doesn't decrease the activation energy at all. And D is, you know, there's more particles to the system, and it's not even more, that many more particles above kinetic energy. This is just creating matter out of nothing. So yeah, has to be A. And then final question now, thanks for sticking with me so long. We've got alkenes react with ozone to produce ozonodes, going to be decomposed to give carbonyl compounds. As you can see here, it breaks the carbon-to-carbon double bond, and it creates 2 molecules with double bonded oxygen. So which of the following alkenes could produce a mixture of ethyl and propanol? So this one, I'm going to go and draw out ethyl and propanol. So ethyl would be something that looks like this. I won't bother drawing out the hydrogens because we don't really need it for this one. And propanone would be something that looks like this. Because there's a ketone, the oxygen would be in the middle, we're in the second atom here, right? So we need to find something. If we join these back together, right, we'll get if we go opposite line here, these 2 carbon atoms would join and be in a double bond, which looks something along the lines of this, right? So now we just need to find a structure that has this kind of thing. So look at here, this does have the correct number of carbon atoms, but it all joins in, this carbon atom is joined to like this, the terminal carbon. So it'd be like if you add the double bond to this carbon up here, so that one's garbage. This one only has 4 carbon atoms, we need 5. Same reason for this one. But this one here has 2 carbon atoms, and it's double bonded to the middle carbon here. So, and then we've got 2 others. It has to be D. Right, thanks very much. I'll be doing the 2019 paper 2 one as well, and I've got a huge backlog of videos that I really need to publish, so sorry about that, I'm just really lazy. But thanks to everyone for sticking around. I'll see you on the next one. MASH out.